Aditya is an assistant professor in CMU in the Department of Statistics and Department of Machine Learning. Aditya's research interests include high-dimensional statistics, sequential methodology, post-selection inference, and uncertainty quantification. And he works in machine learning, neuroscience, genetics, and auditing. Aditya's work has been recognized through several highly prestigious awards, including the Early Career Prize from IMS, Emerging Leader Award from various statistical societies, Bernoulli New Researcher Award, NSF Career Award, Sloan Fellowship in Mathematics, and Faculty Research Awards from Adobe and Google. So that is pretty much all possible junior faculty awards. So Aditya has them all. So without further delay, Aditya, the floor is yours.
Thank you. Thanks for the invitation. Thanks for all of you for coming. This three-part tutorial is about, the grand theme is a Martingale theory of evidence that will become more clear as we go on. But somehow central to all of this is gambling and betting. I'm not going to assume that you have any background in gambling or betting, but by the end of at least today, you'll know how to make money. So I would say pay attention. This is one of the most important things you will learn in your life, how to make money, not things that academics are particularly good at. It turns out that gambling or betting is really central to many different areas. So the ones I'll be talking about the most today are statistics and information theory, but it's somehow fundamentally connected to probability and finance. And I don't mean that gambling and betting has applications in probability and finance, but it turns out that you can define something called game theoretic probability, which is an approach to probability that doesn't proceed via measure theory, but proceeds via game theory instead. So you can redefine all of probability theory using game theory. And gambling or betting is also fundamental to online learning and optimization. That might show up a little bit in tomorrow's lecture, but today's lecture is really going to connect gambling and betting to statistics and information theory, both of which are a priori not really connected to gambling. So what I'm going to do for the first, I think this today's lecture is divided in two parts. For the first part, the three-part series today is about testing. Hypothesis testing. Tomorrow will be about estimation, and then that's tomorrow morning, and then tomorrow afternoon will be about change point detection. So these are three kind of fundamental problems in statistics, and we will show how to take game theoretic approaches towards these problems. But in some sense, today's setting is the most important one. Like if you get the intuition as to why hypothesis testing is in any way related to game theory, today's talk will give you intuition for that, and as well what the connection to information theory is as well. Okay, so within today's talk, the most important part is the second half of the talk. Okay, so the second half of the talk is when I will derive optimal gambling strategies. Okay, so if given a general new problem, like how should you actually gamble in that game, that's what I'm going to derive in part 4. But the first three parts are somehow setting up intuition and notation and stuff like that for building up, and maybe some motivation as to why we even want to get to gambling strategies. So they really are two separate parts. So if I lose you somewhere in the middle of the first part, that's fine. After the break, we can still get back together and look at optimal gambling strategies together. Okay, so in the first part, I'm going to try and motivate why gambling and this stuff is even interesting for statistics in the first place. Like why would statisticians care about this stuff? And in particular introduce this notion of testing by betting and show how it solves some problems that that current statistics has. And then this third part will be the most abstract. So here I'll actually give a very simple example, a running example to show you how you can test a hypothesis by betting. But then the third part will be the most abstract part of the talk. And then after the break, you'll get some coffee, and then we can actually get to the part that's most interesting, which is gambling as well as you can. Okay, so I'm going to start by describing what I call sequential anytime valid inference, or SAVI for short. Okay, so I'm going to start with a very famous controversy from psychology. This is called the power posing controversy, and there's two authors, Amy Cuddy and Dana Carney, are central in it. So can I have a show of hands for those who know what the power posing controversy is? So it's very, okay, like maybe I'm seeing 5 hands or something of that kind. So everyone should know what it is. It's a top 10 TED talk of all time, and so you guys should know what it is. So the claim made in a top psychology journal paper around 2013 or something like that, maybe 2012, was that before giving a talk like I'm giving right now, if I go in private, like to a restroom or something of that kind, and I take powerful poses, okay, then for about 30 seconds, then my performance in the talk is actually going to be much better. So measurably better. They can measure hormones, they can measure my performance in different ways, and it's actually going to be measurably better. And the abstract ends by saying, well, the fact that just 30 seconds of power posing could, or maybe a couple of minutes of power posing, something like that, could yield better public speaking performance, has big implications because many people fear speaking in front of an audience. So that became a very important paper. It became, as I said, a best-selling book, a TED Talk, things with the millions of views. So then people tried to reproduce its findings, and unfortunately, people started to find that most of the findings were not reproducible. And then in 2014, the second author, Dana Carney, she retracted her name off the paper, and she put up a PDF. She's at Haas Berkeley right now, and so it's too small for you to see, but this is a PDF from her website on Haas Berkeley where she explains why she withdrew her name from the paper. And one of the points she says was, initially, the primary decision variable of interest was risk-taking. We ran subjects in chunks and checked the effect along the way. It was something like 25 subjects run, then 10, then 7, then 5. Back then, this did not seem like p-hacking. It seemed like saving money, assuming your effect size was big enough and the p-value was the only issue. So in statistics, this has long been known to be, let's say, a faulty way of doing things. It's called sampling to a foregone conclusion. But let's try to understand what really the issue is. The issue is something called continuous monitoring, and something that scientists want to do with their data. I think every scientist that I know that collects data in neuroscience, psychology, whatever, they are continuously monitoring their data. The problem is you collect some data, which means you increase your sample size. Then you check if your p-value that you have so far on your n samples that you have seen is actually smaller than some threshold. It's smaller than alpha. You peek at your data, and if it is, then you stop and you say, I'm good. You write your paper. But of course, when they wrote their paper, they didn't describe this process. They just said we had 42 subjects. Here's the data. Here's the p-value. But the problem is that if your p-value is not good enough, then you continue and you collect more data, and you do this many times. Okay, so that's really the problem. So with commonly taught p-values that we teach in statistics, the idea of using p-values is that you can control the false positive rate. With probability alpha, you will not reject the null if the null is true. I'll describe what that means a little bit more later on. But with commonly taught p-values, this circular procedure does not anymore have any false positive rate control. You make a lot of false discoveries, and your false positive rate can be much larger than alpha. So more formally speaking, if Pn is a classical p-value that you calculate using the first n samples, this is what it means to be a p-value. It means if the null hypothesis is true, so let's say in this case the null hypothesis is that there is no treatment effect. Like I went and did my power posing and it actually makes no difference. What should be the case is that the p-value is uniform or it's stochastically larger than uniform. So the probability that it's less than alpha equals alpha ideally, but if it's less than equal to alpha, that's also fine. And this is what the definition of a p-value would be. But if tau is the stopping time of an experiment, like so for example, tau typically depends on the data. It might be the first time that your p-value drops below alpha. It's no longer the case that p tau is a valid p-value. So even though for every n, pn might be a p-value, the fact that in this statement, n is independent of the data. For every fixed sample size, you get a valid p-value. But now that you're optionally stopping, the p tau is no longer a valid p-value, and it's not any more uniform or stochastically large. And in fact, this is usually, instead of being less than alpha, it's actually just equal to 1. Now, this is not a problem with p-values. When this stuff came out, people said, oh, p-values are horrible, we should abandon p-values. It's got nothing to do with p-values. The same thing holds for confidence intervals. So people said we should abandon p-values, go to confidence intervals. But there's a duality between p-values and confidence intervals, which is very basic. And so if you draw the same picture over here, and you say, let's say I'm going to collect some data, and I'm going to look at it, and I'm going to check if my confidence interval, 1 minus alpha confidence interval for my treatment effect, if that contains 0 or not. And if it doesn't contain 0, I'll collect more data and I'll keep going, and I'll stop only if 0, which is the no effect, is not in my 1 minus alpha confidence interval for the treatment effect size. And then if I stop, then what I have at the end is not a 1 minus alpha confidence interval. The false positive rate is going to be much larger than alpha. And so again, formally to say what I mean, if I have any classical 1 minus alpha confidence interval that you have learned in your basic statistics classes, then what it means to be a 1 minus alpha confidence interval, let's say we're trying to estimate some kind of a treatment effect in a causal inference randomized clinical trial, something of that kind, what it means is that the probability that theta lies in ln un is at least 1 minus alpha. But this is only true if n, the sample size, is independent of the data. Okay, the problem is when you have a stopping time of an experiment, for example, you stop at the first time that the lower confidence bound is above 0, so you seem to see a positive effect, then L tau U tau is no longer a valid confidence interval. In fact, the probability of coverage is now not at least 1 minus alpha, it's actually usually equal to 0. For typical settings, you get no coverage whatsoever for a stopped for this kind of stopped confidence interval. So what we really want, like in statistics, is some kind of safe, anytime valid inference where we can freely, continuously look at our data, examine it as we go along without violating any properties. So I'm going to just savvy methods are those that yield valid inferences at adaptive stopping times, at any arbitrary stopping time, possibly not specified or anticipated in advance. Okay, so I don't know when I stop. I might stop because I ran out of money, maybe because my boss told me stop, maybe the data looks promising or looks not promising, whatever. No matter how I stop, I should have valid inference. So if I was able to get such methods, if I was able to get a savvy method, then it would allow for continuous monitoring of the data, adaptive decisions to halt or even to continue experiments longer than you had expected for any reason, all without violating the validity of the claims. And if we were able to derive such methods, it would provide a lot of flexibility to the statistician. It would allow you to peak without any issues. Classical statistics does not allow all this, but savvy methods that we're aiming for will make peaking completely legal. And that's very useful for exploratory settings where there's no oversight. So in something like clinical trials, the FDA has oversight where they say, like, pharmaceutical company has to report how the trial is going to run, and they say, well, we'll have 40 subjects and we'll look once, we'll have 40 more subjects, we look one more time, and we'll have 40 more subjects and a third time, and that's it. So you specify a maximal sample size, you specify exactly when you're going to look. So in pharmaceutical settings, you can do that. In academic settings, good luck. Like there's nobody who's going to pre-specify any of these sample sizes ahead of time. Nobody's going to stop you from looking at it. So what you really want is a brand of statistics that is says, okay, that's fine, keep looking at your data, it's okay to do that. Another setting is the tech industry, where again engineers start what are called A/B tests and launch them on and then they continuously monitor the data if they want to, or at least there's no oversight as to how often they look at the data, when they stop, and they're running thousands of experiments. So for example, Amazon and Microsoft are running tens of thousands of experiments at any given point in time, and so there's no oversight for any of this. What you still want is to not make too many false discoveries, right? So that's the goal of like these kind of savvy methods. And the interesting thing is that this goal is going to be achieved by betting. Okay, and so I'm going to now say, well, I've given you at least some motivation from statistics. I haven't told you how to achieve it. The talk will be about how to achieve it. But for now, that's one part of the story, which is statistical inference. Let's go to the other side. Forget about statistical inference completely, and let me tell you a little bit about betting, because I guess most of you don't even know the most basic problems in betting. So let's start with the simplest betting problem, and we're going to go back to a paper by Kelly in 1956. Okay, this is the simplest betting problem out there. Okay, so the setting for this is that in 1948 or something of that kind, Shannon had published his work on information theory. He had defined entropy, KL divergence, all of these things, and but he was motivated by communication. Okay, and Kelly has this paper titled "A New Interpretation of Information Rate," where basically he says that I'm going to forget about communication and those goals. I'm instead going to play a game, and it'll turn out that the optimal gambling strategy in this game, its wealth will be related to the KL divergence or the entropy. And so he says this is a completely different interpretation or motivation for the definition of entropy and KL divergence. It's you don't have to say it arises out of some communication axioms and stuff like that. He says it arises out of optimally gambling in a game. Okay, and that's the title of his paper. So let me tell you what that game is and what the optimal gambling strategy is, because it's extremely simple. Okay, so the setting is that Kelly said, suppose we observe IID coin flips BI, so B for Bernoulli, so it's Bernoulli I, and it has a known bias of P which is greater than a half. So think of P as being 0.6 or something of that kind. Okay, you know this. Okay, now what you're allowed to do as the gambler is you're going to start with $1, and you're allowed to bet some fraction of your current wealth on the next coin. So clearly, if the bias is positive, you'll bet it on heads. Okay, and so Kelly asked the question, how much should you bet on the next coin? Okay, how much should you bet on heads? If you know the bias is 0.6, how much should you bet on heads? Now, if you bet everything on heads, you're going to go bankrupt. Even though it's biased towards heads, in 2 or 3 rounds, the tails will come up and you'll lose all your money. So clearly, you shouldn't bet everything. So how should you bet? Like, what's the right way to bet? You shouldn't bet everything. You should not bet nothing either. You can make money in this game. So how should you bet? So the question is simply, what fraction lambda of your current wealth should you bet on the next heads? Okay, and here's the simple way to derive the answer to that question. Okay, so this is the formula for the wealth after t rounds of betting. Okay, this is an IID game, so it turns out that I don't have to, I bet the same way in every round. I don't have to change my betting. I know the bias of the coin. I do exactly the same thing in every round. So lambda is the fraction every round. So this 1 plus lambda times 2b minus 1 looks a bit funny, but 2b minus 1 is just plus 1 or minus 1, because the Bernoulli is 0 or 1. This is the transformation to make it plus 1 or minus 1. So this formula looks like 1 plus lambda times 1 minus lambda times 1 minus lambda times 1 plus lambda and so on. So it basically, when I got it right, my wealth went up by a factor of 1 plus lambda. When I got it wrong, my wealth went down by a factor of 1 minus lambda. This is the wealth of the game when you bet a fraction lambda in each round. Okay, so essentially in the very first round, if you bet half your money, if you were right, you'd have $3/2. If you were wrong, you would have half a dollar. And then from then on, again, if you did the same thing, and so this is just a multiplicative formula that results from betting lambda fraction of your wealth in each round. Okay, it's very simple. Now, this is an equality that I'm writing down. So this product, just by exponential and log, is equal to the exponential of the sum of the logs. Okay, because the product becomes the sum when I take logs. And by the law of large numbers, because this is an average of IID random variables and so on, this sum actually looks like t times the expectation plus a small o of t term. This is all equality. There's nothing, there's no approximation, there's nothing that I'm making. This is exactly true. And so what Kelly said is, great, my wealth can be made to grow exponentially, and what I should do is try to maximize this exponent of my rate of growth of wealth. So I should basically maximize the expected value of log of 1 plus lambda b. That's what I should do. Sorry, I switched from 2bi minus 1 to bi. Maybe you should call this bi prime, which is plus or minus 1. And another way of saying that is, what I should do is not try to maximize my expected wealth, but maximize my average expected log wealth. And so the reason you need to take log is because your wealth can grow exponentially. You should maximize the exponent. So take log, you'll get at the exponent. So he suggested this, which is called the Kelly criterion, which is maximize your average expected log wealth. In this case, it's very simple because it's an IID structure. Maximizing your expected log wealth corresponds to maximizing just this simple functional in one round. And the optimal answer turns out to be 2p minus 1. Okay, it's, for this problem, it's 2p minus 1. That's how much you should bet on heads. It's very intuitive. Just think about it. If p is a half, which means actually it's not biased, this says don't bet, there's no point betting. If p is 1, this says, well, put all your money on heads. Clearly, if it's probability 1 heads, you're not going to lose, so just put it all on heads. And if p is 0.6, then you should put 20% of your money on heads. Okay, it's reasonable. It shouldn't go all in, and you should not bet. You should bet 20% of your money. It turns out that it's just linear in the bias. It's nice. It's a simple, clean solution. But so far, it doesn't seem to be connected to, information theory yet. What he showed that is when you plug this in, then the optimal wealth process, how fast does your wealth grow? It grows exponentially fast. The optimal exponent is the KL divergence, or the relative entropy of p with 0.5. Okay, so if you have not seen KL divergence or relative entropy, I will define it in eventual slides. But it appears naturally that's the best possible rate of growth of wealth. Yeah.
This is the gives distribution. What is written, right?
Sorry.
This is if I write down the dual problem for the if I write down the Gibbs problem, the one for them for which the Gibbs distribution is the solution.
Sure.
Is it what every time?
Yeah. Yeah. Yes. But I mean, a simple way to see this is just differentiate. This is an expectation under a coin of bias p. This is a parameter lambda that I'm trying to optimize. This is a concave function of lambda. A smooth continuous concave function of lambda. I'm trying to maximize it, differentiate and set it equal to 0, solve that, and you get this solution. And when you plug this solution into the optimal wealth, you just get the KL divergence. That's the optimal exponent. So your wealth can grow exponentially, and the optimal exponent is the KL divergence of p with 0.5.
The whole small part is how much we pay for it's the regret.
No, there's no regret here, because this is really this is just the convergence of the strong law of large numbers, because there's nothing to learn here. There's no p. Like there's no learning going on for you to have a mixture strategy and regret. Nothing. There's nothing. You know P. This is just equality. It's equal to this plus fluctuations of the strong law of large numbers. Yeah. Okay. Okay. So the really takeaway message from this slide is the best possible rate of growth of wealth is the KL divergence of P with 0.5. This is a story that we will generalize significantly, but this is where Kelly started off. Soon after that, Bryman wrote a paper in 1963. This is the same Bryman that hopefully everybody in this room knows for random forests and bagging and everything else that he did in the 90s. But in the 60s, Bryman was gambling. Okay, so he has this paper, Optimal Gambling Systems for Favorable Games. He has several interesting results in this paper. But two things is he says, well, he says you might be interested in other things, like for example, you might want to minimize the time to reach a threshold wealth, or given a particular threshold time, you might want to maximize your wealth, and things of this. You might have other goals in mind, but he basically shows that the Kelly criterion also asymptotically optimizes these other goals. But anyway, he has I think it's interesting to note that Bryman in 1963. Actually, a reason I put this up also here is that it has I think people don't write like this anymore, but it has a very nice introduction. Assume we are hardened and unscrupulous types with an infinitely wealthy friend. We induce him to match any bet we wish to make on the event that a coin is biased in our favor to turn. Anyway, if you read it, it's beautiful to read, and it's like, people write much more boring these days, I think. But maybe he was Bryman and could get away with it, but I like the style of writing very much.
Reviewers have become boring.
Yeah, maybe reviewers have come, I don't know. Okay, so now the question is, how do we tie the two together? I talked to you about statistics and problems with p-values and anytime valid inference, and I talked to you about betting and making money when you knew a coin was biased and stuff of that kind. How do we tie the two together? Okay, so the way to tie the two together is it's really popularized by these authors Schaefer and Wolf. Actually, Robbins in the 1970s was doing this implicitly, but it's this very simple idea of testing by betting. Okay, so in order to test a hypothesis, a null hypothesis, I'm going to transform the testing problem into a game, and this game is going to have two properties. If the null hypothesis is true, no strategy is going to be able to make systematically make money. Okay, so essentially, the null is true means you start with $1 and in expectation you're going to have at most $1. But if the alternative is true, the null is false, then it will be possible to design a good betting strategy that can make money. Okay, so there's some little bit of art in it, but now it's becoming more of a science. But essentially, you start with a testing problem and you transform it into a game. And the game must have two properties. If the null is true, you can't make money. If the alternative is true, there's some way that you can make money. Okay. In that case, wealth in the game is directly a measure of evidence against the null. You start with $1 and you keep betting. If you make $2 at the end of playing it for 10 rounds, I'm not very impressed. If you make $40 at the end of playing 10 rounds, I'm super impressed. Right? It's like, think about going to the roulette, which you think of as being a fair coin. If you multiply your money 20-fold at the roulette table, someone should be surprised. You should be surprised. You should think the roulette is actually not fair. So the idea is very simple, that we set up a game where under the null you can't make money. So if you make a lot of money, the null must be false. So wealth in the game is directly a measure of evidence against the null. The larger your wealth, the more evidence there is against the null. So every strategy of the statistician in this game corresponds to a different estimator or test statistic. So there's a mapping from, we want a test statistic, well, that's like saying I want a strategy. So there are good and bad strategies for betting, just like there are good and bad estimators or test statistics. Okay, so what we're going to do is effectively transform the problem of testing and estimation into the problem of game and strategy design. Okay, and then we'll say, once we've transformed into a game, how do we design optimal strategies for playing that game? So Kelly did that problem for, so essentially what you should think about what Kelly did is, Kelly's game, though he did not pose it in the language of statistics, is the right game for saying the null hypothesis is a fair coin. He set up the game, the odds of the game, such that if the coin was actually fair, you just can't make money in that game. And the alternative is the coin has bias P, and we derive the optimal strategy so that if this is really true, our wealth will grow exponentially fast. Okay, but of course, when we have a hypothesis testing problem and it's written in this way, we don't know which of them is true. We don't know is the null true or is the alternative true. We just play the betting game. If we don't make money, we say, probably the null was true. if we make a lot of money, we say, oh good, probably the null was false and I'm happily able to make an exponential amount of money, you're happy. Okay, so this is effectively what Kelly did, even though he didn't write it in the term of testing by betting. Schaefer and Wolf basically did that. Like they say, well, Kelly was effectively testing by betting. Okay, so any questions about this high level structure? If not, yeah, we'll go into more examples and details soon. Yeah, okay, Shubhada first. And
so in the Kelly setup, does the alternative play a role? I thought that
yeah, it does because we know the bias P. It's a point alternative, we know it's P, and so that's why he could derive the optimal betting strategy for that P. But you can come up with different nulls which are composite, different alternatives which are composite. We will do that now going ahead. Yeah.
If I Google Schaefer and Wolf, would I hit the right paper to read?
Yeah, so there is a paper by Schaefer called Testing by Betting. That's the paper. It's a Journal of Royal Statistical Society discussion paper in 2021. It's a very clean paper. It only handles the point null and point alternative case, but it's like really, if you just want to understand the connection and think about the simplest setting, that's the right paper.
Wolf revisited the pretty recently, right?
He visited who?
Wolf kind of revisited this kind of betting stuff and also connection with S values, whatever E values.
Wolf has been involved with this community for a while. Yeah, I mean Wolf and Schaefer invented game theoretic probability. So they wrote the 2 textbooks on game theoretic probability. They have been flirting with game theoretic statistics all along. But I would say that so they're interested in game theoretic statistics, but they've mostly been kind of flirting with it. Yeah. Now in this tutorial we'll kind of deal with it more head on. Okay, so that's the story of sequential anytime valid inference, and I've told you about how testing by betting can yield this kind of anytime valid inference. I'll give you a very detailed example now. So what I'm going to go into is I'll construct a very simple setting where you can reason through the optimal bets and you can think about why does testing by betting solve the problem that I came up with, and the answer is all martingales and stuff like that. And so let's just get into it with a simple example. Okay, so the example that I'm going to discuss is goes back exactly 100 years. These were 2 participants in my example. One of them asked the other, would you like some tea? And the first one said, no thanks, you poured the tea into the milk, but I prefer my milk in the tea. And then the first one says, what, can you really tell them apart? That's ridiculous. And the first one, she responds, yeah, I mean I can easily tell them apart. So if you don't know the characters, these are Ronald Fisher on the left and Muriel Bristol on the right, and this example is called the lady tasting tea. It's a very famous example because what Fisher did next and what Muriel did next is very surprising, very interesting. So Fisher said, okay, I'm going to test you. Okay, she claimed that she can do this. Well, Fisher said, okay, let me test you. He created 8 cups of tea with the Muriel's eventual boyfriend at the time. The 2 of them made 8 cups of tea. 4 of them had tea in the milk and 4 of them had milk in the tea. They randomized the order and they put it on a table and they asked Muriel to come in and taste all the cups of tea and guess which was which. And as history would have it, she was perfect. She got 8 out of 8. She guessed exactly which one was tea in milk and which one was milk in tea. This is kind of it's a fable, but it's true. Fisher writes it in his book. He's surprised, and he asks, okay, well, how surprised am I? How much can I attribute this just to chance? Could I just say, well, she got lucky? Okay, for example, if there were 2 cups, there's a 50% chance that she got lucky and was just guessing. But there are 8 cups. Okay, so what he says is, what's the probability that a chance guess would be perfect? The answer turns out to be 1 over 70. Where does 70 come from? There's just 70 combinations. 8 cups, 4 of one type, 4 of the other type, 8 factorial by 4 factorial, 4 factorial, whatever. There's 70 combinations, and only one of them ends up being a perfect guess, and all of the others have some number of mistakes. And so there's only 1 in 70 chance that this would be just pure luck. And so this is actually a p-value. So if you don't know what a p-value is, that's a p-value. Can you attribute this to chance? Yeah, there's a 1 over the p-value for this is 1 over 70. And so this is a p-value for the null hypothesis that there is no difference between milk in tea and tea in milk. And it's the first, it's one of the first famous examples of randomization based causal inference, right? So it's essentially saying the only way I can really test this is by introducing randomization, and it's in design of experiments, things like that. So it's 100 years old, 1920s. It's a very famous example for all these reasons. But it turns out that this is not a very good game. the odds were stacked against Muriel from the very start, okay, and I'll tell you exactly why. The probability that a chance guess would yield at most one error is actually 17 over 70, which is 0.24. So there's actually 16 ways of making one mistake. There's only one way of getting everything right, but there's 16 ways of making one mistake, and that's not that impressive anymore. So this p-value of 0.24 looks a bit unimpressive. So essentially what this means is that it means like I can, if she made one mistake, I can say there's a 1 in 4 chance this is just luck. I could have just called it luck, which means that the only way for Muriel to succeed in this game was to get everything right. Like the game was set up such that if she got everything right, then Fisher's convinced, but anything else he says, that's luck. So it's not a very good game. So with the benefit of 100 years of hindsight, I would have designed the game very differently, and actually I did design the game very differently, and I ran it. This is what happens when you're bored during COVID. But essentially, I have an espresso machine at home, so we ran an experiment called The Lady Keeps Tasting Coffee, which is a sequential version of this of the same game, where, well, I tell my wife that let's play a game, and she's very skeptical whenever I suggest anything. But when I tell her it involves coffee, she's like, okay, fine, let's say if it involves coffee, that's fine. So this is my version of the game. What I did was I really did this. It was not with this coin, but I like the coin. I went into the kitchen, I privately tossed a coin. If the coin comes up heads, then I produce 2 cups of, the espresso thing is split into 2 parts, right? So I produce 2 cups of espresso, one with milk in the espresso and one with espresso in the milk. And I present them to her, left and right. And then she tastes them and she guesses which is which. Okay, she says, okay, the one on the left is milk and espresso, the one on the right is espresso and milk. And then I tell her, what the truth was. I tell her whether she was right or not. And then again, I do this the next day, or probably the same afternoon. I do this again, where I flip a coin. If it comes up tails, then I have a different, of course I don't show her the coin. I just present those 2 cups to her, this time in a different order. She tastes them and she guesses which is which, and maybe she guesses again, milk on the left, coffee on the right, and so on. Okay, so this is how the game is going to go. Okay, but the key part of this I haven't introduced yet is betting. Okay, so my wife is going to start off, she's Lebanese, so she starts off with, this is 1 Lebanese lira. I'm not making fun of Lebanon, but it's not worth very much. They went through a crisis, so this is like, because of hyperinflation, it's not worth very much, so we felt more comfortable gambling on 1 lira. Okay, so she starts off with 1 lira, I flip a coin, I present it to her, and then what she does is she says, okay, I'm going to put 20% of my money, which is, in this case 0.2 lira, that it's heads being, it came up one particular way. Now I tell her, no, you're not, that's not right, you're wrong, it actually came up tails, which means it was the reverse. And then her wealth goes down, so she becomes 0.8 after the first game because she was wrong. Okay, and then I toss it again, and then I show it to her. She says, okay, I made a mistake last time, but this time I'm more sure that it's heads. So I put 40% of my money on heads. This time I tell her, yes, you're right, and then her money goes up. So now she has $1.12. And this game goes on. Now the key part to notice about this game, so this game, the wealth process looks slightly different. Okay, there lambda was a constant earlier, lambda is not a constant now, lambda is a predictable bet. So she's going to bet a fraction of her money in every round, and so that fraction is going to be based on the previous round. So the word predictable means based on the rounds 1 to I minus 1, she decides lambda I. Okay, so that's what predictable means. And Ri is just +1 or -1, it's the result of the outcome. Okay, so the wealth process looks like 1 plus lambda I times Ri, the product of all of those. The key fact about this is that if the null is true, the null is there's no difference between these preparations. If that's really true, then this Ri is a fair coin, like meaning it's equally likely to be +or -1 and it's independent of her bets. No matter what she bets, Ri is independent of that. And this wealth process is a non-negative martingale. Okay, so it's non-negative by design. Okay, she cannot bet more money than she has, so her wealth process is non-negative. That's by design. Okay, so that's not the part to focus on. It's the martingale part to focus on. The idea is that if there was no difference between the preparations, then her wealth cannot go after expectation. So if those of you who haven't seen what the definition of a martingale is, the claim is that the expected value of LT given L1 to LT minus 1 is actually equal to LT minus 1. And the proof of this is simple, because LT is just LT minus 1 times 1 plus lambda t times RT. And so if I take conditional expectation of LT given the past, so the expected value of LT given the past is just equal to LT minus 1 times the conditional expectation of 1 plus lambda t times RT given the past. And the idea is that lambda t is a function of the past. So lambda t is random, but it only depends on things that have already happened. So it basically for this expectation is like a constant. And RT under the null has mean 0. It's an equally likely to be a plus or minus 1 if there's no difference in the preparations. So if the null is true, then this is just actually equal to LT minus 1 because I'm multiplying by 1 in expectation. Okay, so this is what it means to be a martingale. So it's very, very straightforward actually to see that this is a non-negative martingale.
I was just trying to understand it's not a math question, but it's more the mechanics of your experiment. So you're saying that if the RTs are fair coins, you're saying there is no difference in your preparation.
The other way around. If there's no difference in the preparations, then the result is independent of her bet and a fair coin. It's a fair coin because I'm making both preparations with equal probability, but the fact is it's actually independent of her bets. She can't look at the cups, taste them and tell any difference between the cups. So she's actually betting after tasting. But if there's no difference between them, then her guess is a random coin flip. Whether she's actually right or not is just chance. The result, which means was her guess right or not, that's pure chance if there's no difference in the preparations.
So is it also what is known as optional stopping theorem?
Next slide. Yeah.
Also, does it matter they're betting after or before tasting? Like, is there
Oh yeah. That's a great question. She can taste and then bet. No, absolutely. Yeah, no, for sure. You first taste and you think you know what's going on, then you bet on. Yeah, you can do that. But before I tell you the answer, right? But the idea is, it's just too trivial. Yeah, you can't bet somehow. Well, in this game you can't bet without seeing what the preparation is, because I show you left and right based on like what's on the left and what's on the right depends on the coin toss. So if you didn't even see that, then there's nothing you can do. Yeah, you can taste it. I guess that's the idea. You can do whatever you want, but if the null is true, actually you're not going to be able to make money. Sorry, one more question was there. Next slide.
It seems that the better you guess, the better you become playing because you consume more coffee.
You consume more coffee? No, there's coffee in both of them. It's just one has milk in coffee, the other one has coffee in milk.
Exactly, so much more caffeine in one of them, right? So keep the right one.
No, the same amount of milk and coffee is in both of them. It's just, do I put the coffee first and then the milk, or the milk first and then the coffee? Yeah, the longer you go, the more caffeine, but we only did one round, one in the morning, one in the afternoon each day. So we were coffee calibrated. Yeah, it's fine. This was during the pandemic. We had a lot of time in our hands. There was no hurry to finish this game anytime soon. Anyway, so actually what really did result is after 10 rounds, Leila made a lot of money. It was actually very easy to tell the difference. We can talk more about this offline. But for the purposes of testing, the key part is that that's the wealth process. Under the null, it's a non-negative martingale. So there's something called the optional stopping theorem, which implies that at any stopping time tau, without restriction, no conditions on the stopping time, the expected value of the wealth at that stopping time is less than or equal to 1. If the null is true, there is no stopping time or betting strategy that can systematically make you money. You start with $1. No matter when you stop and how you play, your end is in expectation at most $1. Okay, that's the optional stopping theorem. Many people know variants of this which place assumptions on the stopping time. You need no assumptions. Because of non-negativity of the martingale, there is absolutely no restriction on the stopping time. Okay, so I can, that's just a well-known fact, and I can point you to a Duret theorem about it or something like that. Anyway, so that's the optional stopping theorem.
I just want to say, you probably know it very well. It's just like maybe not everybody in the audience where the word martingale comes from, right?
There's an entire article by Schaefer about this. It's actually not obvious where the word martingale comes from. People think that, so Schaefer's reference is actually Martigues. Like there's a town called Martigues in France where sailors, it was a port, and sailors would stop there and they would gamble. And one of the gambling strategies was called a martingale, which was actually a double or nothing kind of a particular strategy. So a martingale was, like Schaefer has an entire article just trying to trace the history of this word martingale. I don't think it's obvious, but his best guess currently is to Martigues. But you can ask who brought the word martingale into probability theory, and that answer is actually Wheel. So Wheel he wrote a PhD thesis in 1939 that connected gambling to probability theory formally. He actually did it for some different goal, which I can talk about later. But he introduced in his PhD thesis this following inequality, which is very central in this area. There's only kind of two inequalities to know, and one is this one and one is this one, and they're super fundamental. So this is what's called a time uniform Markov's inequality. So for those of you who know Markov's inequality, LT is a non-negative random variable. It has expectation 1. So the probability that it's at least 1 over alpha is at most alpha. So if I drop the expected value there, then this is just what's called Markov's inequality. It's a very basic inequality in statistics or probability or whatever. Now Wheel's inequality says something holds time uniformly. The probability that there exists any time t at which the wealth crosses 1 over alpha is at most alpha. So essentially if I plot the gambler's wealth, so the gambler, well, that doesn't work, so maybe I'll throw that down. But if I plot the gambler's wealth over time, so this is time and this is wealth, okay, and they start off with $1, and let's say alpha is 0.05, so 1 over alpha is $20. What this says is that the wealth process is going to go up and down, right? So the gambler is going to kind of make and lose money. It's basically saying that the probability that the entire wealth process stays below 20 is at least 1 minus alpha. So another way of saying it is, with probability at least 1 minus alpha, this wealth process, which is Wt as a function of t, is below 1 over alpha. With high probability, the entire process stays below 20, not just at one instant. One instant is Markov's inequality, entire process is Wheel's inequality. The probability that you ever exceed 1 over alpha is at most alpha. So it's basically saying if you're playing a fair game, okay, if you have a non-negative super martingale or a non-negative martingale, which means you're playing a fair game, the probability that you will convert $1 into $20 is at most 0.05, ever. At any point, you can play the game however long you want, infinitely long. The probability that you'll ever convert $1 into $20 is at most 0.05. It's a remarkably powerful, beautiful statement. Sorry, yeah, Ashwin, yeah. One second, yeah, Ashwin, yeah.
So, in your optional stopping definition, even though this is a martingale, you've written it as an inequality.
Yes, it's actually true with inequality. You can show that for this particular problem, if I never stop betting, you can actually show that L infinity, for example, is equal to 0 almost surely. So it's really weird that expected value of LT equals 1 for any t, but actually L infinity is equal to 0 almost surely. And the easiest way to see this is actually if you look at the process where I start with $1 and I kind of it gets multiplied by 3 over 2 or 1 over 2 with equal probability in each round. So let's say that with equal probability I go up to 3 over 2 or down to 1 over, that the multiplier is that. Then roughly my wealth is going to look like 3 over 4 to the power n. So if I play n rounds of this game, I'm going to have 2n rounds of the game, then I'm going to half the time it goes up 3 over 2, half the time it goes down 1 over 2. But I do this enough number of times and I'm really actually going down. So so somehow it's really weird that, yeah, let me write that down. So expected value of LT actually equals 1 for all t, but L infinity equal to 0 almost surely. So it's super weird. So actually for stopping times that are potentially infinite, it's really inequality even though it's a non-negative martingale. Yeah, very interesting and subtle point raised there. Dimitri.
So yeah, the reason I mentioned martingale is that the folktale goes that if you are allowed to borrow, like have infinite money to bet, then you can actually make money.
Yeah, if you can borrow, but you need to borrow an unbounded amount of money.
So
yeah,
that's one thing, right? Because
yeah,
you had these conditions.
Yes, exactly. Yeah. Yeah.
And another thing is that this views inequality, I can understand it as Martingale version of Markov's inequality.
It is. That's exactly what it is. It's a martingale version of Markov's inequality.
Okay.
Yeah.
Martingale version.
Yeah, absolutely. Okay. So the lesson is that, yeah, if the null holds, then Leila is unlikely to turn £1 into 50. So as a measure of evidence, LT, the wealth that Leila has in this game, is directly a measure of evidence against the null. Okay. If the null is true, LT is going to be small with high probability. If LT is large, I know the null is likely false. Okay, so we call that an E process. E for evidence, also E for expectation, because really this LT process is really it's governed by its expectation at any stopping time. And the fact that this holds at any stopping time means she can peak, she can stop early, she can continue the game, she can peak it, doesn't matter. If her measure of evidence is her wealth, and so that's peaking free. Okay, so it's called an E process. If you really want to think in terms of a p-value or something like that, then 1 over the wealth is actually a valid p-value. So large wealth corresponds to a small p-value. So, but it's an anytime valid p-value, which means that you can stop it at any time, and it's still valid even with optional stopping. And if you really want to think in terms of, these are real valued measures of evidence, which means that I don't have thresholds associated with them. But if you really want to say I want a level alpha test, which means that your false positive rate should not be at more than alpha, then you can reject the null hypothesis if your wealth ever crosses 1 over alpha. And then Wheel's inequality tells you that that test controls type 1 error at level alpha. Okay, so you can think about, there's 3 different implications for statistics. One is you get an E process, which is the way I like to think about it. If you want, you can convert it to a p-value or a p process, which is free. You can stop at any time, you can peak, you can extend the experiment, and it's all fine. And you can get a level alpha test at any level alpha if you really want to. So you can, but I like to just think in terms of the first one, your wealth, it's a measure of evidence. So this has really solved the peaking problem, right? So I have set up a test for the null hypothesis such that no matter what you track, look at the data, stop early, continue the game, you cannot create artificially evidence against the null. Okay. So why is this interesting? It gives a simple and clean approach to sequential experimental design. Like I expressed everything in terms of this coffee and TT and coffee, it's fun, right? But ultimately this is a clinical trial. I have a drug and I have a placebo, and if I want to test the drug against the placebo, I can do it in this fashion. I can assign at random treatments and controls, and then I can show you the responses, and if you can guess from the responses whether the person was treated or controlled, then there is a treatment effect. And so there's a very clean translation of everything I said to just how a sequential clinical trial would be done. You can express doubt naturally. So essentially the idea is that like if Layla's not really sure, she can bet conservatively early on in the game, and as she becomes more sure of what's going on, she can bet more aggressively, so she can express doubt naturally. It's very interesting that cooperation between the subject and the statistician is actually allowed in between rounds. So just imagine that, let's say that Layla is really good at drinking coffee and I'm really good at betting strategies. In between rounds, we can actually discuss and say, hey, what are the relevant features? So suppose she's looking at temperature and color and taste and blah, blah, blah. And it turns out actually we can learn over time which of these are relevant features. Maybe we can run a lasso to see which of those features are predictive of the outcome. And then we can discuss in between rounds saying, hey, maybe it's better in the next round to only focus on these features and bet using this strategy. It doesn't matter. We can talk about these things in between rounds. In the next round, if the null is true, there's nothing in our conversation that helped her make money. So somehow like this kind of cooperation is actually allowed in this game, and that's I think quite interesting. Interesting that it aligns incentives, even though the tester and the statistician, the subject and the statistician might have different incentives. It's totally fine for them to cooperate, compete, whatever. You can't violate, these incentives cannot violate validity. It's very flexible. It turns out that you can design many games for the same problem. I chose to do 2 cups in one round, but actually I could have 4 cups in each round, and she could guess on each 4. I could have 3 cups in each round, and one of them is produced one way and 2 the other way. So actually it turns out that you can create many different games, and it's very flexible. And that's nice, right? The space of things you can do is open. There's not one right way of doing things. You can make up the game and extend the game on the fly. Like you don't have to promise ahead of time a maximal sample size or anything of that kind. For example, if the treatment effect is very small or if the difference is very small, you might need more rounds to find it, and that's fine. You can just extend the game longer if you think I need a little bit more time. And the evidence, this is actually a really interesting point, but the evidence actually depends only on what did occur and not on hypothetical worlds. So it turns out that a problem with p-values I can discuss offline is that it requires reasoning about hypothetical worlds that did not occur, but in an e-value is like a sequence by sequence measure of evidence. It only depends on actually what did happen, not what you would have done if other outcomes had occurred in other worlds. You just need to reason about what actually did happen in your world. So the actual evidence against the null it's very simple and clean to interpret. There's no philosophical issues with it. Okay, so it addresses kind of 3 issues of p-values, which are peaking, optional continuation of experiments, and reasoning about hypothetical worlds. Okay, so that kind of at least sets up, I give you one example of testing by betting, in this coffee and so on. But now I want to go a little bit more abstract and present some simple concepts to you, slightly more. Let me formally define some concepts to you, and then we'll break. And when I come back, I'll tell you about optimal gambling strategies. Okay. So when I've talked about hypothesis testing a lot, but this is finally what I mean by hypothesis testing in statistical practice. So the null hypothesis is a set of distributions script P, okay, that is defined on some filtered measurable space. Okay, you have some space omega f. The alternative hypothesis is some other set of distributions that's defined on the same space. Okay, so whenever I say null, I mean a set of distributions that I think describes reality. The alternative is some other set of distributions that potentially describes reality. When we are testing H0 against H1, we are basically asking, is the data coming from a distribution in P or is it coming from a distribution in Q? That's what we are asking. And nothing IID is assumed in this notation. Like, even though maybe the games were that way in the notation that I have now, these distributions could be over sequences of observations. So they could be dependent, they could be non-stationary. There's nothing in this. You could still be testing H0 against H1. And in statistical practice, the null has a special role. The reason I say this is because there are communities that kind of treat the null and the alternative as almost interchangeable and look at type 1 error plus type 2 error as a measure of performance. But no, in statistical practice, the null has a special role. It often corresponds to something like no effect. And rejecting the null may actually correspond to making a discovery or have some real scientific consequences. And so what the first goal actually is to calibrate or control the errors under the null. That's what I really need to do. And I'm not looking at total error. I'm first saying I need to control the error under the null. Okay, that's important because people have different views of what hypothesis testing is. So that's this backdrop going forward. Okay, so a P process, I mentioned it previously, but what is a P process? If I'm testing a null hypothesis that P is in script P is the data generic distribution, I'm testing if it lies in script P. It's actually a sequence of P values such that at any stopping time tau, the probability that P tau is less than alpha is less than alpha. Okay, so the main difference here from a usual P value is that it holds at any stopping time tau. That's called a P process. So what is an E value? An E value is really a one round bet. That's what you should think about as an E value. So an E value for the null is a zero infinity valued random variable such that for every P, the expected value of R E value under P is less than or equal to 1. So you should think of how much did you multiply your wealth by after making your bet. So the idea is that if the null is true, no matter what null distribution might be, you should not be able to multiply your wealth by more than 1. Okay, so that's what this constraint is really saying. And so it's called an E value because it stands for, it's a measure of evidence against the null, and also because it's the constraint is not a probabilistic constraint, it's an expectation constraint. We're trying to say something about its expectation.
So could we also look at the power of...
We'll get to this, yeah. I'm defining, that's why I said there's a special role for the null in statistics, and so I'm going to start by talking about things in the null, and the alternative will be optimality. Optimal gambling strategies after the break is about what to do under the alternative, yeah. Okay, so that's what I mean by an E value. So under the null, you should not be able to multiply your wealth by more than 1. And an E process is this wealth process that I had over time. It's a sequence of E values such that at any stopping time tau, the expected value of E tau is less than or equal to 1. Okay, so this is an anytime valid E value in some sense. We call it an E process. Okay, so this will be our evidence process that we're going to try to build up. So some simple examples for simple nulls. Okay, if our null is just a point null P, then essentially likelihood ratios are E processes. So if you're not seeing a likelihood ratio, that's what it is. A likelihood ratio is a ratio of the likelihood of some alternative Q to our point null P. This is an E process. In particular, it's a non-negative martingale. It's non-negative because likelihood ratios are non-negative, and it's a martingale because if I take the expected value under P, then the P cancels out and I integrate Q, which is a density, so it integrates to 1. Okay, so essentially this is the simplest E process. It has expectation at most 1 at any stopping time, that likelihood ratio. Now for composite nulls, that's where the situation actually gets interesting. So for composite nulls, there's 3 things that happen. Okay, you could have non-negative martingales. So what is a composite non-negative martingale? So when you open a textbook, you only see point-wise non-negative martingale. So this is actually a new concept. So you have it's called a test martingale for script P for a set of distributions. If it's non-negative, its initial value is 1, and it satisfies the martingale property for every P in the class. So it's a simultaneous martingale. So it's like usually if you open any probability textbook, there would be only 1 P. and the martingale property is with respect to that one p. But now I'm asking for the martingale property to hold simultaneously for every p. It's a very interesting object. So that's a composite non-negative martingale. Sometimes you can't find them, you can't find these, but you can find composite non-negative super martingales, which means that the same thing, like except that this holds with inequality. So your wealth can, what this means is that your wealth can only go down in every round. You're playing some kind of a betting game, your expected wealth can only go down in every round. Okay. Again, the new part here is the for all p. That's the part that's really new. If you look at the definition in a textbook, it's for one p, but I'm going to look for things that are simultaneously super martingales for every p in some class. But it turns out that e-processes are more general than that. So this concept of an e-process asking for expected value at a stopping time to be at most 1 is more general than these two. These are special cases which are very nice, but they're actually more general concepts. Okay, so why do we like them? It's because if you want a theory of evidence, they should be able to, it should be easy to combine evidence, and somehow e-process is very easy to combine. So if you have dependent e-processes, then averages of e-processes are e-processes because they're defined by expectations, and so expectation is a linear operator. This is not true for p-values. Averages of p-values are not p-values. Products of p-values are not p-values. But if you have independent e-values and you take their product, you get an e-process. If you have dependent e-processes, then you can average them. So essentially averaging under dependence, multiplication under independence makes a kind of clean and simple way to combine evidence, but this is not true for p-values. Yeah.
Is it the class of all non-negative super martingales for a given distribution class state p? Is this set convex?
Yeah. Yeah, because convex combinations of super martingales are super martingales.
So this is a half space constraint.
Yeah. Yes. That's right. Yeah.
So you said that for all p, that is an important thing. So you said that martingales may not exist for all the distributions.
Meaning the only martingale might be one. Like if I, sometimes the class script p is so rich that if I looked for a simultaneous martingale, the only one that I find is one. That's the only one. And so like non-trivial ones don't exist.
And the same thing would
so an example would be sub-Gaussian distribution. So if I give you script p is the set of sub-Gaussian distributions with mean less than equal to 0, something like that, I can prove that there is no martingale other than one for that class. But there is a non-negative super martingale for that class. But there are other problems for which there is no non-negative super martingale. So for example, let script p be the set of all exchangeable binary sequences. Okay, so any exchangeable binary sequence that's allowed in script p, I can prove there's no non-negative super martingale for that class, but there is an e-process for that class. So that's just very interesting. It's for every class. It has to be simultaneous for every p in script p. Yeah. Yep.
So what are some examples of like e-processes which are not?
We'll get to that. Yeah.
Is there already one polar transform in this slide?
Is there what?
Already one polar in the bipolar? I'm asking because p doesn't have to be convex.
Yeah.
But for any class script p, the class of non-negative super martingale
is convex. Yeah. And so there is a bipolar for which there's an effective null hypothesis. We'll get to that. We will get to that. We will get to that. We'll get to this point. So there is an effective null hypothesis which is the bipolar. Yeah. Yeah.
Aditya, the non-curly p, the regular p, you pointed out earlier that either it can be an IID distribution or it can
not.
be,
Yeah.
Can be a Markov chain.
Yeah, it could be something else. It could be something else. Yeah.
Okay.
Yeah. P is a distribution over sequences of observations. It need not be a product distribution. Yeah.
I'm really sorry but that's really interesting to us. So when I say that it is convex, right? So
but let's get back to this convex stuff later. Like I feel like it's really like it's too we'll lose people. So convexity will come up in the second half very centrally, but not, let's forget that right now. Yeah. Okay. Yeah, I think in the interest of time, I'll just skip what Wheel did and so on. And so I think we should just take a break for 10 minutes. I've at least introduced the basic definitions of super martingales, given you an example. But what I really want to get to let's come back at 3:10, and I'll spend the rest of the time telling you what the optimal gambling strategies are when you have composite nulls and stuff like that. Yeah. Okay. Thank you. To the second part. So now we're going to go through this process of actually taking a general problem and transforming it into a game, and then playing that game optimally. So we did that with Kelly betting, and we did that with Layla's and my coffee game, but now we'll just see how to do that a little bit more generally. So we're going to start off with the simplest setting of point nulls and point alternatives, because that's where you have to start. If you don't know how to play this game, you're not going to play more complicated games. Okay, so So the null hypothesis is that is that the data is coming, let's say this is the IID setting for now for simplicity. Actually there's nothing here that needs IID, but for your help you might think about the data as being IID, but otherwise you can just think of x1, x2, x3 as coming from a particular distribution P, and the alternative is that it comes from some distribution Q. And for now we're going to just assume that P and Q are absolutely continuous with respect to each other, okay, so which means that we can define densities and so on. So I have this very classic and simple game, hypothesis testing problem. How do I transform it into a game? Where's the game in this problem? Okay, so this is the game. I have to start with an initial capital of $1. At each round, I have to declare a bet. A bet is a mapping from outcomes to 0 to infinity. Okay, the outcome is script x, some real value, let's say, and 0 to infinity is the multiplier of my wealth. Okay, so that's what a bet is. It's just a function, a measurable function from x to 0 to infinity, a non-negative real valued measurable function, such that under the null I can't make money. So under P, the expected value of st of x given whatever has happened so far is less than equal to 1. Okay, so I first declare my bet about the next outcome. I'm betting on how it's going to turn out. Then reality reveals xt. Okay, then I actually see xt. And then my wealth becomes my previous wealth. I start off with $1. It becomes my previous wealth multiplied by st of xt. St of xt is my realized bet. The bet is a function. The realized betting score is really how much. This could be larger than 1 or smaller than 1. If it's larger than 1, I made money. If it's smaller than 1, I lost money. Okay, so that's the game. Okay, this is the constraint that it's fair under P. I shouldn't be able to make money under P. So now the question is, what is the optimal thing to do under Q? Right? Under P, the game is set up so that I can't make money under P. I can only make money under Q. So the question is, what is the optimal betting strategy? And again, the right notion of optimality is actually log optimality. And I think I already mentioned this before, but if the alternative is true, it turns out that you can make your money grow exponentially, and the right thing to do is optimize the rate of growth of the exponent. That's the best thing you can do. And this is an equality, meaning that the wealth equals the exponent, the exponential of the sum of the logs, which is t times the expected log plus small o of t. So it's like, you know, you can't get around, there's nothing special about log that, I mean, I can't say let me put some other thing in there. It's only log that satisfies this. I mean, the wealth process being multiplicative in this fashion means log comes in very centrally, and Thomas Cover was making this point, I don't know, 50 years ago. So it turns out that the optimal betting strategy, the log optimal betting strategy in this game is exactly the likelihood ratio of Q to P. So you should think about this. What I'm going to tell you is the analog of Neyman-Pearson for the betting world. Neyman-Pearson is a solution that likelihood ratios are optimal if I'm measuring things by type 1 error and type 2 error. Here I'm not doing type 1 error and type 2 error. I'm doing the expected value has to be less than 1 under the null, and the expected value of the log wealth has to be optimal under the alternative, and the optimal answer is still the likelihood ratio. Okay, it's beautiful, it's simple. Okay, so what do I mean by that? The optimal bet is a function from x to the positives. So this is what the bet looks like. St of x is just q of x divided by p of x. It's non-negative. Under p, it has expected value 1. Right? That's the property of a likelihood ratio, is that under the denominator distribution, it has expected value 1. So it is satisfied by that. So the actual realized wealth process is simply the likelihood ratio process. So once I see the data, I just calculate the likelihood ratio process. That's actually the log optimal wealth process. So it is a positive martingale under P. It's like it's strictly positive. It's a test martingale under P, which means at any stopping time, it's an E process. At any stopping time, its expected value is less than 1. If I apply Jensen's inequality, I also get that the expected log wealth is less than equal to 0 under the null. But under Q, the expected value of the log wealth is actually strictly positive, and it is actually maximized by this choice of bets. That exponent, the expected value under the alternative, is actually just the KL divergence between Q and P. So we saw the results for bet where it was the relative entropy of P to 1/2 and so on. It's a more general observation. The optimal exponent of your wealth is the KL divergence between Q and P. Okay. So if you want to look at the point null and point alternative paper, I wrote a lot about it. So let me prove this to you, because it's very simple. It's extremely simple. This fact, let me prove it to you in just 2 parts. Again, it's like an analog of Neyman-Pearson. So the first realization is that, okay, I'm just going to drop this conditioning for simplicity. Okay, so I'm just going to drop that conditioning over there, condition on the past and so on. So I have to declare this bet with less than equal to 1. So the first thing to notice is that every admissible bet must hold must satisfy this with equality. Okay, and the reason is simple. If you did not satisfy this with equality, meaning you had a bet that was strictly less than 1 under P, then I can define another bet which is your bet divided by the expectation, so that now my new bet has expectation 1 under P, but now I have a strictly larger value under Q. So the expected value of log Q of S tilde T is the expected value of Q of log ST, plus this extra term over here. I mean minus this extra term here, but this is less than 1, so it's additive. So anyway, so you can only improve your wealth by making sure you meet the constraint with equality. That's the first step, to realize that effectively equality must hold. Now the second, so what does that mean? So what it means that every admissible bet holds with equality means this: integral of st of x p of x dx is 1. That's what it means for this to hold with equality. So let's just call st of x p of x, let's call it rt of x. Okay, let's just give it a notation rt of x. So this then means that rt of x is a density, like it integrates to 1. It's positive and it integrates to 1. So it means that if I rewrite this equation, st of x is rt of x divided by p of x for some choice of rt of x. It is a likelihood ratio for some choice of rt of x. That means every valid bet that's admissible is actually just a likelihood ratio, meaning if it holds with equality, it must be a likelihood ratio. And now you can ask, what's the best likelihood ratio? What is the best thing I can do for rt of x? The answer is put q of x in there, and that's just Gibbs inequality. So my claim is that if I look at the expected value under Q of any the log of RT of x by P of x, this is the growth if I bet according to RT of x, but somebody else bets according to Q of x, they're going to do better than me. Their growth rate is actually going to be better. And the reason of this inequality is because P of x just goes away, and if you reorganize this is just the non-negativity of the KL divergence. Okay, so it reorganizes to saying the KL divergence is non-negative. So if you reinterpret this, it's saying that Q by P is better than any other bet RT by P. Okay, so this is a two-step proof to show. Firstly, any bet is dominated by an equality. Equality means it's a likelihood ratio. The best likelihood ratio is Q against P. That's it. We are done. Okay, that's the proof.
So for this is for point alternative.
Yeah, point null, point alternative. That's what I started on the previous slide. Point null, point alternative. You have to start there and understand that case well. If you understand that case, everything else is a building block. Okay. Any questions about why the likelihood ratio is kind of the best thing for point nulls and point alternatives? Yeah.
Can you be a little bit more precise about the claim of optimality? So you're doing it in this particular log wealth sense?
Yeah, that's right. So it's log optimal, but as I said, the wealth process WT, which is a product of this ST of XT, this is actually just equal to the exponential of the sum of the log of ST of XT. This is equality, and this is actually just equal to the exponential of the t times the expected value of log of ST of x, whatever the sum. If you did something differently in each round, then it's a sum, but for a point null and alternative you don't have to, plus small o of t. So this was just Kelly's observation, is that somehow these are just equalities, and so if you really want to have the best possible wealth, you need the best possible exponent which corresponds to the expected log wealth. So you need to optimize the expected log under the alternative.
Is it going to be true?
It's always true. There's nothing like your wealth is always going to be a product of how much you bet and make in each round, the multipliers of your wealth. This is just always equal to this. This is true. So for all betting games, this is just true. This was actually Cover's point. Cover spent I think 30 years arguing that log is the right utility for betting games. There were he really insisted that log is really the right thing, and it is the right thing, because I'm not making any approximations when I write this down. This is just really always true. Yeah.
Are you assuming IID here to make this?
Yeah, this last step is, no, this is not IID, but this step of saying the sum is like the expectation is like IID, but otherwise it would be the average of the expectations. It's still true with this still concentrates around the average of the expectations plus a lower order term. So it's close enough.
At that point, it wasn't clear for anybody, so you can have chain of inequalities for any monotone function, not only for log. But
No.
the log is
Yeah.
a function that makes it into the sum. Right? So it's also
Oh yeah. If you really want to understand your long-term behavior, it's only the log that concentrates. Like this concentration only happens with the log. Yeah. Yeah, I can always apply inverses and so on, but the concentration, if you really want to understand what your wealth looks like, you look at its expected log. Okay, so now we know what to do for point nulls and point alternatives, and here I want to bring up, many people brought up the word power in their questions. This is a difference between the E world and the P world. In the P world, we judge tests by their probabilities. We try to maximize the power of a test subject to the type 1 error control being less than alpha. This is actually a theory of decision making. We are trying to make a decision, 0 or 1, is it null or not, and so on. But what we are trying to do in the E world is not decision making. This is a theory of evidence, E for evidence, okay, and we are really judging E values by their expectations. So under the null, we are judging it by what is the expected wealth under the null. We are calibrating that to be 1 so that you can compare things easily. And under the alternative, we are looking at expected log wealth. So we call this E power or growth rate of the wealth. And this is a theory of evidence. So we're looking for a real, we're not trying to make a decision. It's a complementary theory. We're not trying to replace Neyman Pearson. If you want to make decisions, that's the right thing to do. If you want evidence, a theory of evidence, a real valued measure of evidence which grows with time, which you can extend and add studies onto and things of that kind, then we think this is kind of the right way of doing things. So somehow we're designing a complementary theory to, say, Neyman Pearson. So whenever you see an E value or E process, you should ask about its E power or its growth rate, not its power, which is really a P concept. It's loss in transforming from one to the other. It's not hopeless, but let's say it's not the goal. Our goal is to think in terms of. Okay, so now let's change the things to say, well, okay, now what if I have a simple null and a composite alternative? Okay, which the way to think about this is like there's a forecaster that claims the world is described by P. There's a skeptic that thinks no, actually it's described by Q theta for some other theta and wants to bet against the forecaster. Okay, so because it's a point null, this likelihood ratio idea is going to be maintained, but the alternative now, I don't, you say I don't know what the right alternative is. There's kind of only two options. One option is to mix or to hedge your bets with some prior pi. Okay, so this is like you can think of it almost like a Bayesian point of view, but like hedging is really a financial concept. Okay, if you maybe for simplicity, if you think there are two alternatives, Q1 and Q2, what this is saying is put half your money on Q1 and put half your money on Q2. Okay, that's just when you see an integral with respect to d pi theta, it's just mixing, which is just averaging. Since each of these by themselves is a martingale, a non-negative martingale, an average of non-negative martingales is still a non-negative martingale. So that property is still maintained. That's one thing you can do. Another thing you can do is you pick a plugin. So essentially, after you learn, you use the first I-1 samples to pick a particular theta hat I, and you plug that theta hat I into, so you take likelihood ratios of a particular Q theta hat I against P. So you pick a representative of the alternative and you go on. So these two are actually very closely related, and what you can show, and I won't get into it too much because I want to get to the real point, but what you can show quite easily is that under very, very little regularity assumptions or so on, you can show that either of these strategies is adaptive to the alternative, which means that the growth rate that you get under some Q star is what actually generates the truth. So under the null, you're not going to make money. Either of these is a non-negative martingale, you won't make money, that's fine. Under the alternative, you look at under some Q star, you don't know Q star, but you're following one of these strategies. It turns out that the achieved growth rate using either of these two strategies, so WT does not know Q star, the achieved growth rate will actually be the same as the optimal oracle growth rate. So an oracle that knew Q star would just bet according to Q star divided by P, and this would be their growth rate, and we asymptotically achieve the best growth rate anyway. So this is like it's instance adaptive. So no matter what Q star is, it's going to adapt to that and get you the right growth rate. And so it's kind of well-known regret property of the method of mixtures. It comes up centrally in Cover's regret analysis and so on. But it's a much more general property of the method of mixtures. And somehow the intuition should be simple. Like if the reality was two options and you didn't know which one and you just mixed, under world 1 your wealth grows exponentially, and what you would have is half that wealth. So you have an exponential, but you have half that wealth, but half the wealth also still grows exponentially. So it's like you don't pay really much of a price for not knowing. Learning somehow is simple in this kind of a setting. Yeah. Sorry.
This brings me back to my previous question.
Yeah.
Growth rate is fundamentally an asymptotic concept in data, but these two strategies clearly behave differently, presumably.
Yeah, you can write down more finite sample regret rates, and they'll have similar regret also. Okay. Yeah, and they'll have logarithmic in the log scale. They'll have logarithmic regret, and it'll be you can write that down for both of these strategies. There's so it's nice.
So one quick question.
Yeah.
If you go back to option 1, option 2, it seems like option 1 is kind of like a Bayesian perspective,
Yes.
and option 2 is frequentist. Is there
No, they're both frequentist. They're both because they both have frequentist validity, meaning under the null, under any element of the null, actually in this case it's point null, but under the null you have exact type 1 error control. So somehow you're Bayesian under the alternative. That's the key. Like somehow the game theoretic view is a middle ground between Bayesian and frequentist. So what it says is under the null you should be frequentist, and under the alternative you should be Bayesian.
Right. No, that makes
And-
sense. I agree that the guarantee you showed was frequentist.
Yeah.
I was curious if you can like show links. Like
No, the very strong links. There's actually an Annals of Statistics paper by Robbins and Siegmund in 1974 that shows that confidence sequences, which I'll talk about tomorrow, arising out of this type of a strategy exactly asymptotically match confidence sequences out of this type of a strategy. And so there's at least stemming back to Robbins 1974, Robbins and Siegmund 1974, these two strategies are very closely related. Yeah, this is a Bayesian strategy in disguise, because actually it turns out if it'll achieve this growth rate. The condition for pi is it should put mass everywhere. Okay, that's the basic condition for pi. And what about theta hat I? I can't be stupid and have theta hat I just be a particular theta for all time. So the right thing to do here is a posterior map estimate. Like you actually have a prior, you have some data, and then you calculate your posterior mean and you plug that in. So it turns out that it's the same kind of if you use the prior here to instead plug in using a posterior mean, this will have the same property as that one. So that's why there's a relationship, is because the right way to pick a representative is to be Bayesian there too.
Yeah, that makes sense.
Okay, so to summarize what was known to test a point null against point alternative, likelihood ratios are optimal per round bets. The optimal wealth is the likelihood ratio process. The optimal rate of growth, the exponent, is the KL divergence or relative entropy between Q and P. And now the question is, what about composite nulls? This is actually the most important question in statistics. We don't want to test point nulls, we want to test composite nulls. Okay, so so there was significant progress made on this by Peter Buchwald and co-authors in 2 papers. One was safe testing, a JRSSB discussion paper, and one was a more recent preprint online. And so what I'm going to do, I'll tell you what they did, but we complete the story and I'll tell you what that story is now. Okay. So this paper we just recently put on arXiv like a month ago. The title is the numeraire E variable, which I will define, and the reverse information projection, which I will define. And it's joint work with 2 professors of mathematical finance, one at CMU, Martin Larsen, and one Johannes Ruff at London School of Economics. Okay, so our setting here is actually composite null versus simple alternative, because somehow dealing with a composite alternative is not hard. You mix with the Bayesian strategy, it's actually fine. So the difficulty actually is, if I have a composite null script P and a point alternative Q, that's the interesting problem. So which means the data is drawn from some P in script P, in which case we say the null is true, or it's drawn from Q, in which we say the null is false. Okay, and a valid bet is an E variable, which is any non-negative X, such that the expected value is less than or equal to 1 for every P in script P. Okay, so X is the multiplier of your wealth in each round of a game. So we're just going to ask the question, in one round of the game, what's the optimal way to bet? Okay, so the question is, what is the optimal 1 round bet X star? Okay, so one observation, you're going to bet once. What's the right way to bet? Is it unique? Is the optimal 1 round bet, is it unique? Can we characterize it and derive it and so on? Okay, and so it turned out that the answer to this question is, it is the likelihood ratio of Q to a very special element P star that we call the reverse information projection. And I'll define what that means and what the story is. Now, and our work basically, it tells a complete story about this pair X star and P star. X star is the optimal bet, P star is this reverse information projection. They're a dual pair, and we tell a complete story about this pair. Okay. Now, if you might say, I don't like testing and I don't think about statistics. Okay, this is the setting rephrased in terms of betting. Okay, so there's a set of possible outcomes omega. The forecaster claims that script P describes the world well, which means that the outcomes or events are described well by some P in script P. A skeptic thinks that this forecaster is bogus and believes that Q is a better model for the world. The forecaster offers bets based on the forecasts. Says because he believes that script P is the forecast, he says you can bet against me using any random variable such that if my forecast is correct, you shouldn't be able to make money. And then skeptic is going to pick a particular bet X, and observe the outcome omega, and the skeptic relies on that as x of omega, and so which bet should the skeptic pick? Okay, so this is the same story. This is in the Kelly world of the in the Kelly formulation of the world, where it's not involving null and alternative, but this is the same. It's the same story, but you can think about this just as a gamble. I need to make an optimal gamble against a composite null. How do I do that? Okay, and the answer is, again, it's the log optimal bet x star is the likelihood ratio of q to a particular to the reverse information projection p star. Okay, let me introduce these characteristics. What is x star, this numeraire e variable? Okay, so the main result which is interesting is that under absolutely no assumptions on the null and alternative, okay, which means we need no measure theoretic assumptions. We don't have to assume that script P is a convex set, script P has densities, there's a reference measure, nothing, absolute continuity, nothing. Under no assumptions on script P and Q, there always exists a special e variable x star which satisfies two properties. First, it's exponential, so it's actually non-negative and it's less than or equal to 1 under the null. But the main property is the numeraire property, which is that under the alternative, the expected value for any other e variable x that you could have picked, the expected value of x by x star is less than or equal to 1. The expected value under Q of x by x star is less than or equal to 1. So roughly we want it to be larger under Q, right? So this is basically saying if you pick anything else, x star is going to be larger than that, meaning that if you take the ratio under Q, it's less than or equal to 1. So we call this the numeraire property. Further, this particular optimal bet x star, it's actually unique up to Q null sets, and in fact you can also show that it's the numeraire if and only if it's log optimal, which means that by log optimal I mean it also satisfies that the expected value under Q of log of x by x star is less than or equal to 0 for any other e variable x. And so this is actually a consequence of this by Jensen's inequality. So if you take this and you apply Jensen's inequality, you get that. I think I wrote that down. By applying Jensen's inequality, you get two other interpretable consequences. You actually get that the expected value under Q of x star divided by x is greater than or equal to 1. This is just another way of saying x star is better than any other bet x under Q. But if you apply Jensen's with log, you get this statement. The expected value of log of x by x star is less than or equal to 0. Okay, so all these three things are true. And this statement is actually this is a cleaner way of writing things down because it avoids some issues with log. Okay. Yeah.
So I didn't understand what you mean by uniqueness, because if
it's unique up to Q null sets, which means the x star is a random variable, and it's like I can muck around with it on Q null sets, but otherwise it's unique. There's only one e variable that is better than every other e variable in this sense. That is, if x star 1 satisfies this and x star 2 satisfies this, then x star 1 is equal to x star 2 almost surely under Q.
But then if I set the null to be simple.
No. You fixed script P and you fix Q for a fixed problem.
Okay. So it's unique.
X star depends on script P and Q.
We can talk about this after.
No, I mean the optimal bet depends on the null and the alternative.
No, that's fine. But
yeah.
In your previous thing you said I can basically mix with a prior or I can sample on a posterior. These are two separate.
No, this is a point null. Point alternative Q.
Okay, sorry.
The composite null and point alternative Q. Yeah. You can deal with composite alternatives later by mixing and stuff like that, but I have one Q and I have a composite null script P. That's the hard part.
Sets of measure 0.
Yeah.
Aditya, quick question. So earlier we were talking about why log is important and all that stuff, right? So every time you're trying to do maximization of this expected log, can you always write it like this?
Yeah, it turns out that this is actually the first order KKT condition of this problem. That's what it turns out. Yeah.
I see.
But
This property has nothing to do with point or composite nulls and alternatives. This is always true, going from this to that.
Yeah, this to that. Yeah, exactly. Yeah. But I mean, it fixes Q, so it's true for composite alternatives. Sorry, composite nulls, but it's for a point for a particular Q, right? So I'm fixing Q. Okay, so that's what X star is. I'll tell you more about X star soon, but there is an X star. There is an optimal bet. It is unique. It's better than every other bet in multiple different senses. and it's uniquely defined for any problem. Okay, so what about P star? Okay, so this reverse matrix projection, we're going to define a measure P star. It's actually a non-negative measure, it's not a probability distribution in general, but we're going to define a measure P star by defining its likelihood ratio to Q. Okay, so if you haven't seen this before, it might seem a little bit odd, but I'm trying to identify, I'm define, this is a definition of P star. I say, what is P star? Well, it's a measure whose likelihood ratio with respect to Q is 1 over X star. Okay, that's the definition of P star. So if X star is infinity, then this likelihood ratio is understood to be 0. Also, by definition, P star is absolutely continuous with respect to Q, which I think just by construction. And again, by definition of P star, we have that X star is a likelihood ratio of dq to dp star. Okay, again, I just cross multiply and I get X star is actually just d. It's not cross multiplication. Really, anyway, you really get this by definition. It turns out that I'm going to write my numeraire, which always exists, as a likelihood ratio of Q to some element P star. I'm going to define that element P star that way. And in general, P star is not a probability measure, it's a sub-probability measure, meaning it integrates to something less than 1 in general. Okay? And you can ask, where does this element P star lie? It turns out that it lies in what's called the bipolar of P. So, this is a duality of, there's a duality story going on between sets of distributions and sets of key variables. So, this concept of E variables and stuff like that, it doesn't appear out of nowhere. It's like, it's actually turns out to be fundamental. If you've ever heard of the polar of a set, well, the polar of a set of distributions is the set of E variables. So, the polar of a set of, if I give you a set of distributions, the polar is the set of non-negative random variables such that the dot product between x and p is less than or equal to 1. So, this expected value of x under p is the dot product of x and p is less than or equal to 1 for all p in script p. So, this is the definition of polar, and that's actually just the set of E variables. So, somehow the polar, in convex geometry, the polar of our set of distributions is the set of E variables. And now if I take the bipolar, which is I take that set and I look at its polar, I get back to the set of distributions in quote because it's now non-negative measures, such that the expected value is less than or equal to 1 for all x in the polar. So, this is the polar is a set of E variables. I take any E variable and I ask for any non-negative measure such that this is true. So, this is actually what's called the Fenton null hypothesis. It's very close to the convex hull of script p, but it actually contains the convex hull of script p. It's larger in general than the convex hull of script p, but I'll get back to that later. But anyway, the point is this P star, we can show that P star lies in the bipolar of P. Okay, why is this interesting? It's interesting because of a particular theorem that I'm going to write down, which is a strong duality theorem. And for the rest of this talk, I'm going to, for simplicity of writing things down simpler, I'm going to make the assumption that Q is absolutely continuous with respect to script P. Q is a particular distribution. It's absolutely continuous with respect to script P, which is a very weak assumption. What it's saying is that if P of A equals 0 for every P, then we also have Q of A equal to 0. Okay, so if there's a particular event that is impossible under the null, then it's also impossible under the alternative. It's a very weak assumption, because if it's not true, suppose there's some event that's impossible under the null and it's possible under the alternative. If that event happens, we can immediately reject the null because it's impossible under the null. And so effectively you can actually get infinite wealth on that event, and so it kind of leads to some trivial corner case. So this is actually really without loss of generality. You can treat that kind of corner case separately. So it's a very weak assumption, but it will help. And the KL divergence, which I think we have seen a few times, but it's if Q is absolutely continuous with respect to P, then the KL divergence is defined this way, and it's otherwise defined as infinity. But it will turn out that there's like actually another way of defining things which is actually more useful for us, which is if PA denotes the absolutely continuous part of P with respect to Q, you can actually write the KL divergence without having these two cases. You can just write it as minus log of the Radon-Nikodym derivative of the absolutely continuous part of P with respect to Q. Anyway, this is a minor point, but so you don't have to deal with infinities. You can actually deal with this definition of KL. Okay, so here is a strong duality statement which holds without assumptions, but I'm stating it under this very weak assumption. But actually, we have a version in the paper which holds with no assumptions. So let X star be the numeraire, and let an element of the bipolar that's equivalent to Q. then the following statements are equivalent. So the first statement is P star is the Ripper, the way we defined it as, dP star by dQ is 1 over x star. This other statement, these have some interpretations. This is actually what's called the description gain of if the data is coming from Q and you describe your data according to P star, switching to any other element of P is always negative. So there's an information theoretic thing called description gain is non-negative. But if I say that the description gain is non-negative, that's actually non-positive, sorry, this is actually equivalent to saying P star is the Ripper. So anyway, the following statements are equivalent, but the more important part is that if P star is the Ripper, so if x star is the numeraire and P star is the Ripper, then one has this very beautiful strong duality statement, which is that the expected value of the log x star under Q, which is the growth rate that we are looking for, is the largest possible value of the growth rate if I maximize over any E variable, which is the polar of P. It's equal to the sup over all E variables of the expected value of Q of log x, which is equal to the infimum over all P in the bipolar of the KL divergence of Q to P, which is achieved by P star, which is equal to H of Q P star. Okay, and it turns out that these could be infinity in some cases. That's fine. If any of these is infinity, then all of these are infinity. Okay, and but the duality doesn't stop holding. Okay, it's a very clean statement. So essentially, x star is the numeraire, P star is the Ripper, and the best possible growth rate is given by the closest element to Q in script P, measured by the KL divergence. So the reverse information projection is, the picture for the reverse information projection is you have some set script P, you have some outside of script P in general, but it's in the bipolar. Okay, it's outside script P, but that larger thing is the bipolar, and this KL divergence is minimal among all it's achieved. So meaning this H of Q P star, even though P star is a sub probability measure in general, you can define KL divergence same way. This achieves the minimum infimum KL divergence to everything else in the bipolar, and this value of the minimal KL divergence is the optimal wealth growth rate among all E variables, and that's achieved by the numeraire. Okay, so it's a very general duality statement, tells you the relationship between gambling and information theory, maximizing the growth rate and minimizing the KL divergence. That story is very general and needs no assumptions, literally no measure theoretic assumptions, and so I'll show you it's actually interesting. But anyway, some history, it goes back to a PhD thesis by Jonathan Lee, who was Andrew Barron's PhD student in 1999. And so can't see it from there maybe, but in his work he defines a new information projection theory. It's interesting that it took 50 years after Shannon to write down the new information projection theory, which is this infimum of the KL divergence with respect to its second argument. So the word reverse is the fact that you're taking infimum with respect to the second argument. But in their work, they actually define the reverse information projection differently. They say they have a convex set of measures and they have densities. So a common reference measures, they have densities, and they define the reverse information projection if, as the infimum is finite, they need this infimum to be finite, and then they say, well, if I can find a sequence of densities which converges the log densities converge in some L1 sense, then they define the reverse information projection. So it turns out we don't need the KL divergence to be finite, we don't need the set of densities to be convex, we don't even need densities in the first place, and if you add these additional assumptions, our definition of Ripper matches this definition of Ripper. So it's really the right definition of Ripper is ours, which specializes to this one when you have additional assumptions. And they prove that these certain properties that I wrote down on the previous slide are actually characterizing properties, but they proved it only in some kind of special case. So this is a snapshot from his PhD thesis in 1999. But more recently, Peter Grunwald and collaborators once again have a generalization of this. So they took Jonathan Lee's work and they generalized a little bit, but they still needed assumptions where they say they have firstly absolute they need everything to be absolutely continuous with respect to a common reference measure. So you have densities, they need the set to be sigma convex, which is closed under countable mixtures and things of this kind. Anyway, so our theory completely avoids any assumption at all and can still have this strong duality theory holding. Yeah, you have a question? Yeah.
So I believe that everything we're discussing now will be generalized to other variances.
Yeah, I'll talk about that on the last slide to Rennie, and then I'll talk about the difficulty to F going on. So I'll get to Rennie at the end. The last slide is Rennie. Okay, so here's a little bit more about the bipolar. So you should think of script P as just some set of distributions. You should think of the bipolar of P as kind of the convex hull, but little bit more general. And yeah, this is the statement that I showed. That's what P star is, some element of script P. Okay, so little bit more characterization. So if M1 is a set of all probability measures and M plus is the set of all non-negative measures. So there's this word solid, which is a set is solid if every time there's an element in the set, a smaller element is still in the set. Then you can prove that, what is this element called the bipolar? Well, we can show that if script P is finite, then the bipolar, if I take the set of probability measures in the bipolar, it's actually the same as the convex hull. So it's only, that's when script P is finite, and there's a common reference measure. But more general, I mean, when it's finite, there's always a common reference measure. But when script P is infinite and doesn't have a common reference measure, the bipolar is the right object to be dealing with, and not the convex hull of the distributions. Yeah, okay, I think anyway, some more fact, it's just some interesting convex duality comes up here, which is interesting. Yeah.
So even when P is finite, this bipolar may include these non-negative measures that are not probability measures.
Yeah, it does. Yeah.
Is there an intuition or an example of?
Yeah, we'll get to that. Yeah, simple examples coming up. Okay, a little bit more about X star and P star. This X star is dq by dp star by definition of P star. And here's an interesting fact. So if you take let's say you start with some e variable X star, and you define P star by dp star by dq is 1 over X star. It turns out that X star is the numeraire if and only if P star is in the bipolar. Okay, you started with some e variable, you defined things this way. If the thing you got was in the bipolar, then actually what you started with was the numeraire. So it's actually a characterizing property of the numeraire. So some facts like the numeraire is q almost surely positive, P star is equivalent to q. It's the only e variable which can be written as the likelihood ratio of q to some element of P. So somehow this is a concept of a generalized likelihood ratio. In statistics with composite nulls, we don't know how to deal with likelihood ratios. It's not well defined. But here is a unique and general definition. Our numeraire is the only e variable which can be written as dq by dp star for some element in script P. It's the only one. And in fact, it's also maximal, meaning like even if it's a sub-probability measure, it is not dominated by any other element of the bipolar. So it's something very interesting about dq by dp star. There's something very interesting. This is a generalized likelihood ratio for that set script P, and I think that's a very interesting concept. Okay, so first example, symmetric distributions. I think this is very interesting. So let's Z denote the data. In this case, we have not really given notation to the data yet. In this case, it's real valued. And my null hypothesis, which is composite, is all symmetric distributions. Okay, so distribution like probability distributions such that Z and minus Z have the same distribution under P. Okay, so this is a very rich set. It contains discrete distributions, continuous distributions with any support. In particular, there's no reference measure for this class. You cannot define densities. It has no dominating reference measure. You cannot define likelihood ratios on this class. Now suppose for simplicity only that Q has a Lebesgue density. You have some alternative, and let's say it's not symmetric. It turns out that the older theory did not apply in this case, because everything in the older theory needed a reference measure and things of that kind, but here our theory does apply. We can easily show that the symmetrization of Q multiplied by some indicator is actually the Ripper density. And in fact, if it's very interesting, if you want to see, this is a particular case where it's a sub-density. If Q is one-sided, so suppose you have a one-sided alternative, meaning it has a density that's only supported on the positive reals, then this Q of minus Z is always 0, and the Ripper is actually just Q over 2. So it's weird. You start off with an alternative Q, and your Ripper is Q over 2. Okay, and that's fine. That's a probability density. The Ripper is a probability density if and only if Q has symmetric support, and we can show that this is actually the numeraire. That's a bet. That's the optimal bet that you can make in this case. It's an interesting bet. It seems you're taking the likelihood ratio of Q to its symmetrization, and it turns out that's the optimal bet in this case. Okay, so we generalize beyond the Lebesgue density in the paper. Yeah, sorry, there's a question.
Just a quick question about what do you mean by reference measure?
Yeah, because you have discrete distributions with any support and continuous distributions with it's like you cannot define densities. Like that's what I mean. So if to define a density, you need to have a reference measure like the Lebesgue density, like the Lebesgue measure or the counting measure or something like that to be able to define densities. You need densities to define likelihood ratios. And so it feels like you can't even define likelihood ratios. It feels like you can't define KL divergence when it comes to how are you dealing with KL divergence with a class of symmetric distributions. It's ridiculous. I have things that are not absolutely that are singular with respect to each other. I have discrete and continuous distributions that are singular with respect to each other. How can I even start to talk about KL? No problem. This is fine. This is the Ripper. This is the reverse information projection. It's unique. This is the numeraire. It's unique, and you can do testing, and it's perfectly fine. So that's the interesting part about all of this theory. It kind of gets around the fact that it seems like you shouldn't even be able to define things to start KL to start out with or something like that. And the way we get around going to E variables. So somehow the set of distributions is ugly, no reference measure and all that. No problem. Go to the polar, which is a set of E variables. That's nice. It's just non-negative random variables. It's a convex set, things like that. And somehow dealing with E variables is the right way to deal with sets of distributions without a reference measure. Another simple example is sub-Gaussian distributions. So let's take sub-Gaussian distributions with negative mean. Okay, so if you have this is the sub-Gaussian definition of a random variable being sub-Gaussian and having negative mean, and so this condition implies that your mean is less than or equal to 0. And now for simplicity, take an alternative like normal mu1 for mu greater than 0. Okay, so I have a point alternative with positive mean, and all my distributions are sub-Gaussian with negative mean. Now again, the sub-Gaussian class is one for which there is no reference measure. You have discrete and continuous distributions in the sub-Gaussian class with any support, and so there is no reference measure, so you cannot apply the older theory. But it's actually very simple to show that this is the numeraire. Like it's a very simple closed form expression. That's the numeraire. It's actually the likelihood ratio of the Gaussian normal mu1 to the Gaussian normal 0,1. That's actually the numeraire. And normal 0,1 is actually the reverse information projection. So even though this class is very rich, in this case the numeraire is actually just a probability density. Here's another example, a cute one from a different paper. I'll tell you why it's interesting. So there's only two nulls, normal 1, 1 and normal minus 1, 1. Okay, that's the null. It's just 2 points. And Q is a centered Cauchy distribution. Okay. The reason this is interesting is because the KL divergence of a Cauchy to a Gaussian is infinity. Okay, because Cauchy has exponentially heavier tails than a Gaussian. So if I take the likelihood ratios, whatever, anyway, so the KL divergence of Cauchy and Gaussian is infinite. So it seems like what can you do? No problem. Yeah, and that was the point I was making. The reverse information projection is still well defined. It's actually just P1 plus P2 by 2. So that the simple average of those two is the Ripper, and the numeraire is just this. So somehow betting, testing, everything is still clean. You don't run into these issues of infinities and reference measures, no problem. So it actually enables you to do things in new cases that we couldn't do things before. In all cases, not new cases, in every case, but some of them are easy to describe. And then yeah, you can do this for one parameter exponential families and things of that kind. I won't get into it. So the last thing I wanted to mention was like Dimitri brought up F divergences. So here's a beyond, you can go beyond logarithmic utility. I don't think it actually is well motivated from betting perspective, but from the math you can still do it. So suppose you consider a more general optimization problem, which is the expected, find the E variable which maximizes my utility for some continuous increasing concave differentiable bounded U. Okay, so continuous makes sense, increasing makes sense, concave makes sense. I mean, increasing because the more money I make, the more utility. Should have concave like log, that makes sense. Utility usually concave. Should be differentiable so that I can actually do something interesting. Anyway, so one interesting example comes when you have a power like x to the power 1 minus, anyway, these are power utilities rather than log, which I dealt with. Log was unbounded, but we dealt with it separately. These utilities are anyway. So we can show that even if you switch to these utilities, no matter what you had about your, under no assumptions on your set of distributions, a maximizer, a best variable for this always exists and is unique, and this Renyi projection P star gamma, rather than if we define a Renyi projection, we take the Radon-Nikodym derivative of dP star by dq and we set it equal to this quantity, then it's still unique, and we have a duality theorem that says, well, x star gamma and P star gamma, they satisfy, they do attain the strong duality statement that if I ask for the best utility in x over script p, and then there's like a little transformation of the Renyi divergence the infimum, the smallest any divergence and the best possible E variable are related by some simple transformation. But this is the definition of any divergence. It matches the KL divergence when gamma equals 1. Otherwise it's just another divergence. And so anyway, so you can define Renyi numeraires and Renyi projections if you wanted to, and all of this theory still does go through. It's unique and it's well defined, the strong duality still holds and so on. Okay, so to summarize, we have fully generalized Kelly betting to composite nulls and point alternatives that yields a strong duality between X star and P star. We have defined this reverse information P star and this optimal E variable X star without any assumptions. We showed how to apply this theory to new non-parametric settings that were out of reach before. We showed how to generalize this story to general utilities that have some conditions. And the next steps are, we're looking at doing this for even more general utilities like unbounded F divergences. Composite alternatives, as I said, you can handle through mixing, sequential betting strategies and so on. So we have some ideas for all of these. Might have applications to EM and covariate shift, because I don't know, one of the steps is like a proxy for maximum likelihood and like a KL projection, but now you can do it without having a reference measure. So I don't know, might have some implications for EM or covariate shift when you don't even have reference measures, or you have things that are not absolutely continuous with respect to each other. You can maybe, so that's really a little bit more open. Okay, so let me, I don't think I have time to really get into this stuff. Let me just summarize. So testing by betting is a very simple framework for hypothesis testing that yields sequential anytime valid inference. Optimal gambling strategies are always based on likelihood ratios. Composite alternatives are handled using mixtures. Composite nulls are handled using reverse information projections. You can describe this, but instead of doing a reverse information projection, you can actually just take maximum likelihood under the null. That also works, and that's called universal inference. But that's kind of a weaker solution. If you can solve for the reverse information projection, it's actually better than taking maximum likelihood under the null. And then non-negative super martingales are actually secretly likelihood ratios. So even when you don't have reference measures, sometimes you can define non-negative super martingales, and they play the role of likelihood ratios. So they really are, non-negative martingales are Radon-Nikodym derivatives. And E-processes, this thing I defined, they exist more generally. Even when there are no non-negative super martingales, sometimes you can define these E-processes, and they're actually necessary and sufficient for sequential testing. Okay, so let me stop there. I'm happy to take any more questions, but let me stop at this point. Thank you. Yeah, Dimitri.